No problem. You can put the.
All right. Magandang gabi. Good evening, engineers. Welcome to another session, another edition of Even Learning. Thank you for joining us today for the Acmv series. We are glad to see you participating in this seminar. This seminar or this training is brought to you by Even Learning. Even Learning provides quality training and seminars conducted by your peers. So for tonight, our training is about Acmv controls. Acmv controls, correct? For this training, you will learn mostly how the airside controls are being done and how the water side controls are being done. Also, the auxiliary systems within the Acmv. This training session is estimated to last for about an hour, including the Q&A. As we go along, you may have questions. Feel free to write your comments or write your questions on the comment sections below. For those that are in Facebook, you could write it on the comment section on Facebook. We will get to them during the Q&A portion. Should you have questions remain unanswered, we will get back to you after the training. Or you can send me an email at evenlearning.sg@gmail.com. My name is Donny Gabriel. I am a professional mechanical engineer with more than 20 years of experience in designing and installation of air conditioning and mechanical ventilation systems for various applications. I am an alumni of Mapua Institute of Technology. Okay, so let's start our training na. Let's start our training. So I'll share you my screen. All right. Oops. There we go. Okay, so for tonight, our series is the last one, the Acmv controls. We are going to wrap up how we're going to control the things that we have designed in part 1 to 4. So when all these services are installed, how are we going to control them? What is the logic of how to control your ACM, mainly your air conditioning system? So overview of the air conditioning and mechanical ventilation. Again, my name is Tony Gabriel. I'm a professional mechanical engineer. You could reach me at evenlearning.sg@gmail.com, or you can use my mobile number. My mobile number is 93895128. I am based in Singapore, so +65. So for tonight, we're going to learn 3 things. Airside controls, or how you're going to control your mechanical ventilation. Water side controls, your chilled water side, your chilled water system, and other auxiliary systems installed within your Acmv system. So it's not all just your fans and your blowers and your chillers and your pumps. There are also other systems within the Acmv system. Okay. Right. So first, airside controls. Let's have an example. This is your room. You have a small room. You put your air conditioning unit on, you installed your air conditioning unit, and it's hot. So what are you going to do? You would get your remote control and then you turn it on and then you put on your settings. So your input will be your conditions. You want your room to be 16 degrees or you want your room to be 24 degrees, up to you. And the output will be the control action. What will the the equipment, or what will the aircon do so that it will achieve the conditions that you have set. Okay. So let's see an example here. Airside controls. Example, you have multiple rooms, you have multiple offices, and you installed one big air conditioning system, one big air conditioning unit, centralized. Okay. How are you going to ensure that all of these rooms have enough air, have enough supply, so that the room will be cooled down? In our previous example here, when you are hot, you'll just increase the air speed. You put from low to high. If it's too cold, you put into low. If it's too high, if it's too warm, you put into high. But on this system, where there are multiple rooms, each person would have their own set point or their own setting. How are you going to do that? So, for example, wait a minute. Into options. There you go. So, example, one room has 10. This room has 10 cmh, or 10 cubic meter per hour requirement of air. And all of this will be 10 cubic meter per hour. So all of the rooms will require 10 cubic meter per hour. Example, this guy that sits here tends to work very less, goes home early. So this guy will turn off his aircon. So what is this unit going to do? So this unit is sending out 80, 10, 20, 30, 40, 50, 60, 70, 80. So there's eight rooms, 10 cmh each. So assuming that this air conditioning unit is sending out 80 cubic meter per hour of air to all rooms, except for this one. How is this aircon going to know that it needs to go up or go down, or ramp up or ramp down, or speed up or speed down? Okay. So first of the airside controls is the pressure sensor. So this pressure sensor monitors the pressure within your main duct system. Okay. So this pressure sensor is monitoring the pressure on the main duct. So this pressure sensor kind of looks like this. Ensures that on this point, there's a constant pressure. This pressure will be able to maintain the pressure across all the ducting system. So even though that this guy over here closed his aircon unit, all these other guys will still have enough air. So how will this unit know if it's going up or going down? So if this pressure sensor, for example, we put a set point of 10 Pascal. If this unit is running at 100%, this pressure sensor will read 10 Pascal. If one room closes, turns off his unit, turns off the supply, and is still giving 80 cmh, the pressure here will go up. The system now will recognize, oh, the pressure goes up from 10, maybe now becomes 12. I need to tell this variable speed drive to slow down. Hey, slow down. This variable speed drive will be connected to your fan motor. So this fan motor speed will lower down. Thereby, the fan will also lower down, and thereby the volume of air will also be lowered down. Question?
Possible.
So James, do you have a question?
The problem.
Okay. No, so no question. Okay. Oh, where are we? So this pressure sensor, for example, this room closed down. This pressure sensor will go up. The pressure sensor sense an increase of pressure, telling this variable speed drive to lower down or speed down, so that the volume of air will be lowered down, maintaining your pressure set point. Okay. This process or this flow is called control logic, the logic of which how you control your equipment. So example here. So this is the start. When you turn on your equipment up to here at this point. Assuming this pressure sensor now is maintaining at 750. There you go, 750 Pascal. 70 Pascal. Is the current duct pressure lower or higher? If it's higher, yes. Is the current speed 50 hertz or higher? Yes or no? Then assuming that it is no, then increase the speed. So this is the control logic. This is the logic how this equipment will react. Up or down, stop or slow, stop or start, whatever it may be, whatever action you want to do, this control logic will have to determine that. Now, this control logic is located inside your PLC. So what is a PLC? A PLC is a programmable logic controller. It's basically a small computer where you put your logic in. So all this logic, all this decision making, all these conditions, all this monitoring, and the appropriate action or appropriate decision that needs to be made are stored in a PLC. So this PLC is standalone. So this your pressure sensor is just sending out signal to evaluate or to interpret this signal is the job of a PLC or a programmable logic controller. And this PLC will tell other equipments what to do. So the signal from your pressure sensor will go to a PLC. Then the PLC will evaluate and will tell the VSD what to do. This VSD will tell the motor what to do. Sometimes this PLC has an option to bring out the signal or to show the display to a remote area, to a remote computer. So this remote computer only shows the display or only has the access to only has a remote access to a PLC. Okay? This remote access, or we call it supervisory control, or sometimes we call it SCADA system. Okay? So a lot of PLC can go to a single remote unit. It's called a SCADA system. Okay? Again, the control of an equipment starts with your control logic. This control logic is housed inside a PLC. This is your heart of your control now, your PLC. This PLC monitors your devices and gives appropriate action to other devices so that your set point will be followed. There is also another one, building management system or building control system, automated control system, or sometimes it's called BMS. So BMS now, instead of having a rugged standalone mini computer, this BMS now directly puts their signal into their system, and then they using control language. There you go. Standard control language such as BACnet, Loanworks, and Modbus. The signal goes to the DDC or digital controller and goes to the main server where the logic is stored. So now you only have one area where all these signals are coming from, and all the signals are going out to other equipments. This pressure sensor and this VSD are called field devices. So these field devices are the ones monitoring and controlling your equipment. So these field devices are one, monitoring the conditions of your equipment, then giving these conditions to your BMS or your PLC. Then the control logic will evaluate these conditions and will send out appropriate signal to other field devices so that the conditions for your monitoring devices are always met. So other things that are being monitored by the BMS are sometimes the ventilation, the lighting, the power system, firefighting systems, and security systems. So not only the ACMV, no, if you're using PLC, is one piece, one PLC, one unit, one PLC. But if you're using a BMS, not only your entire system, but other systems can go inside the systems. Question? No question? Right. Other controls for the air handling units. Another one, differential pressure sensors. Your air handling unit has differential pressure sensors. There's one here controlling a sensor, which means monitoring the before coil, or we call it on coil, and after coil, or we call it off coil. So on coil and off coil pressure difference. We're also monitoring the pressure difference between the coil and the mixing box, where the before and after the filters. And we're also monitoring the damper actuators. So this sensor, the pressure differential sensors, for example, this sensor first. This sensor is determining the pressure difference between filters. Usually, your filter manufacturer will say, this filter has a pressure drop. So this pressure drop is when the air passes through, so that we can capture all this dirt or all these particles. This pressure drop will have 100 Pascal. But over time, this dirt will accumulate. So your pressure drop will increase. The manufacturer will say up to 250. When your pressure drop is 250 Pascal, which means you need to replace your filter. So this differential pressure sensor will monitor that. This pressure differential sensor will monitor the difference between the before and after of filters, so that when it reaches the threshold or the limit, it can send a signal to your BMS or to your SCADA saying, hey, alarm. So which means your filter needs to be cleaned already, needs to be replaced already. Same with the coil differential pressure sensor. The before and after of the coil are being monitored, so that you would know, because not 100% of the particles are absorbed by are left or captured by the filter. Some of the particles are still within the air, and when it touches the cold or moist or wet coil, it gets stuck to the coil. So the coil becomes dirty and it needs periodic cleaning. This differential pressure sensor between and after the coil will tell you when to clean the coil. So it also sends a signal to your BMS telling, hey, this is the pressure drop of the coil. You need to clean already. Another field device within the AHU is your on-coil and off-coil temperature sensor. This on-coil and off-coil temperature sensor will only look like this. Will tell you what is the heat load being transferred to the room or from the room. So you will be able to know what is the cooling capacity, what is the cooling requirements of your area. So this on-coil and off-coil temperature sensor will verify your cooling capacity or your performance of your air handling unit. And of course, you have your damper actuator. Or this damper actuator usually are hardwired to your air handling unit. It will tell your air handling unit, it will tell your BMS if it's closed or open. So because when the air handling unit is turned off, this actuator usually is also closed. When it's turned on, this actuator will open up. So this is on the operation of the air handling unit. When this actuator is closed, the unit is off, and when the unit is on, the actuator will open up. Okay, this is a Magna Helic gauge. So there's different types. You have your analog type Magna Helic gauge, and you have your digital type. So sometimes this one digital type. So there's also a digital type of pressure differential sensors. Another one of your airside controls is your cooling tower. So how do you control your cooling tower? Your cooling tower also have a variable speed drive. You put your temperature sensor here. Again, where is this one? This is when the cold air goes up, it has contact or heat exchange between the water vapors or water droplets, and after that hot air goes out. So you want to measure this hot air temperature. So based on the hot air temperature, you put your temperature here, you'll be able to send a signal to your BMS, and your variable speed drive will increase or decrease the frequency of your fan motor. When, example, let's say your cooling tower manufacturer says the delta T is about 5 degree Celsius. So 32 and 27. So when the cold air comes in, hot air comes out. So it says 27 in and supposed to be 32 out. So if the air temperature is less than 32, which means this variable speed drive will ask the motor, hey, you're working too hard, you can lower down a bit. You can slow down. But if the if the temperature here is higher than the set point, higher than 32, that the variable speed drive will tell the motor, oops, I think you're a bit lazy. You need to ramp up a bit, run faster. So this temperature sensor, depending on the temperature set point, will tell the BMS. The BMS will will evaluate. If it's lower than the set point, the variable speed drive will lower down. If higher than the set point, this variable speed drive will ramp up or increase. Just take note, the variable speed drive is measured in hertz. In the Philippines, if I am not mistaken, the standard for motor frequency in the Philippines is 60 hertz. In Singapore, it's 50 hertz. So you need to check your local standards. In Singapore, it's 50 hertz. In the Philippines, if I remember correctly, it's 60 hertz. So that's it for our airside controls. Any questions before we continue? For cooling towers, there's another option. Instead of measuring the temperature for your outgoing air, you can also measure the temperature of your outgoing water. You can see here, hot water goes in. You can monitor your cold water out. If for example, your set point for cold water is 26. If your set point is higher or lower, if the actual condition is lower than your set point, then your variable speed drive can lower down. If it's higher than your set point, your variable speed drive can go up. So that's another way. You get the same effect if you monitor your air or your water, provided that you're controlling the same equipment, the cooling tower fan. So there's more than one ways, no? Some people will go with the temperature sensor on the air, or some people will go with temperature sensor on the water. It doesn't matter. As long as you write the correct logic, it can go with the air and you can go with the water. But just make sure that you're measuring the outlet side. Air out and water out. So that's our air side controls. Let's go with the water side controls. Water side controls. So here's another example. This equipment, we're cooling down one office and there's a temperature sensor. Let's say the temperature sensor says it's too cold, but we need the airflow here. The airflow is required. We cannot lower it down because of the fresh air requirements. If we lower down the quantity of air, which means your fresh air will also be less, which means it's not an ideal condition. So instead of lowering down the quantity of air, what we can do is to lower down or to control the chilled water going in. So this temperature sensor now can this temperature sensor or this room can be monitored through the return air duct system. So whatever the temperature here is the same temperature that goes to the duct is the same temperature that goes here. So this temperature sensor now will be the signal for this one will be sent to the SCADA, and then it will control your motorized valve or your chilled water valve. So this is a chilled water motorized valve, what it looks like. So this same principle, when the room is too cold, this valve will close down. When the room is too hot, this valve will open up. Okay. But this side, this motorized valve will need a valve assembly. So this valve is not alone. It has other brother, sister, cousins to help him so that the water here can be effectively controlled. Okay. What are included in this valve assembly? So, example, this is your air handling unit. This is the valve assembly right over here. This is your control valve. So this is your valve assembly right here. So it's not shown complete, no? This is a fan coil unit. This is the valve assembly. Right? So for every air handling unit, for every fan coil unit, you have a valve assembly or a set of valves and fittings so that this air handling unit can be controlled effectively. Okay. What are those that are included in the valve assembly? So this is an example of a valve assembly. This is a typical valve assembly. So each company, each industry have their typical valve assembly, but this is what I personally use. Okay, what I personally do, what I personally install. Okay, this is my typical AHU fan coil unit, chilled water cooling coil, valve assembly. So what are these items here? This is a flexible connection. For your valve assembly, you need a flexible connector. This flexible connector so that the vibration from your air handling unit and fan coil unit will not transfer to your piping system. Remember, your air handling unit has a fan. This fan is vibrating when it's in operation. So you don't want this vibration to transfer to your rigid pipes. These pipes are rigid and they are installed and fixed. You don't want vibration to be going through them or else your installation will get loose. So you put a flexible connector so that the vibration is isolated. Then you have your drain points. These drain points, although in actual operation doesn't really have any use, but it has a big use when you are installing the system. When you are installing the system, this drain point is very, very useful and very, very important. So don't forget to put your drain points. Okay. Balancing valve. Balancing valve is a flow restrictor, similar to a control valve. What's the difference between the balancing valve and the control valve? The balancing valve limits the amount of water permanently that can pass through. So when the water goes here, there's always a fixed amount or a measured amount, preset amount of water that can pass through. The rest is being held or stopped. Then you have your Y strainer. Your Y strainer is there so that you can clean the debris or the dirt in the water will not go to the coil. You can take it out and you can clean it up. This is for your maintenance and operations people. Then you have your isolation valve. This isolation valve you have here. This isolation valves is to isolate this whole system. And you also have isolation valves here. These three isolation valves is so that you can isolate your control valve. So anything that happens to this control valve, it gets faulty, it gets short, it needs to be repaired. Then you have your bypass line. This coil can still be in operation even though this is being maintained or faulty by the bypass line. And you also have your isolation valve so that you can replace this one whenever it needs to be replaced. These pressure and temperature gauges or pressure and temperature sensors are there so to confirm the conditions of your system. To confirm if you're getting enough water, to confirm if you're getting enough cooling capacity within your system. Okay, so this is your air handling unit and fan coil unit valve assembly. So this one, valve assembly. Okay, so how does it being controlled? So now the temperature here, previously we said we're controlling this motorized valve based on the temperature sensor of your return air duct or the temperature condition of your room. Just like the cooling tower, there's also two options. Either you monitor the air temperature or you monitor the water temperature. It will also give you the same effect. By monitoring the water temperature, you'll be able to determine if the motorized valve needs to be closed or needs to be open or partially closed or partially open according to your set point. Again, your set point is being monitored by your temperature sensor, temperature gauge. The signal is being sent to your BMS or your PLC where your control logic is located. And those signals are being analyzed so that they can send appropriate signal and appropriate action to your motorized valve. Okay, next. Chilled water side. Assuming now that you have 4 numbers of air handling units, and you have 3 chillers. Why 3 chillers? Like our previous example, you have 2 duty, 1 standby. To ensure that the water is enough for all the air handling units, you also have a pressure sensor. Now, this pressure sensor ensures that these these pumps are supplying enough water to all air handling unit. But like our example before, this one air handling unit is in maintenance mode or turned off. What are we going to do? So if this is turned off, the pressure sensor will detect an increase in pressure, and this three-way valve will bypass or will release the extra pressure back to the chiller. Another way of doing it is with VSD again. This pressure sensor, same logic, this pressure sensor will sense an increase or decrease in pressure when this air handling unit is turned off. When this air handling unit is turned off, this pressure sensor will sense, oh, too much pressure, will send signal to the BMS or to the PLC. The PLC will then send a signal to your VSD telling the pump, hey, lower down your speed. We have too much pressure already. This will ensure that there's enough flow to all the air handling unit while only giving the appropriate amount of flow, not too much. Okay. Next, same scenario with your cooling tower side. Your cooling tower side also has pressure sensors. Same scenario again. When one of the chiller is turned off, so the cooling tower the pumps will receive a signal from your BMS or from your PLC saying that the pressure is too high, the pumps need to lower down, need to slow down through the VSD. Okay. Earlier, we were talking about the air handling unit and the fan coil unit valve assembly. Now this is the valve assembly for your pump. So this is the symbol of the pump. So inlet, outlet. Again, isolation valve to isolate your pump. So anything that happens to the pump, you can dismantle the pump, close the isolation valve, your system is still working fine. Your system can still work without one of the pumps. You can do all your maintenance and your installation works or repair works as needed. Just like before, you also have your flexible connectors. So this pump, since it's running, it's vibrating. We don't want this vibration to transfer to your rigid pipes. That's why you put your flexible connectors. Since we're dealing with same inlet temperature and same outlet temperature, there's no change in temperature within the pumps. We don't put the temperature gauge anymore. We only put the pressure gauge to know the inlet pressure and outlet pressure of the pump so that you can verify if the pump is running as per desired. Based on the pump and based on your electrical power consumption, you will be able to gauge or you'll be able to have an estimate. You can plot it on your pump curve. What is the performance of your pump? Again, drain points. Don't forget your drain points. During operation, drain points are kind of useless. But during installation, drain points are very, very important and very, very useful. Wise strainer to ensure that there's no debris going to your pump. This debris, even though small, tends to destroy or tends to damage your pump. So that's why the wise strainers are important. That's why pipe flushing is important before within your pipe installation. And last one is your check valve to ensure that there's only one way flow. There's no backflow of any fluid to the pump. It will damage your pump. Backflow will damage your pump. And the check valve will also keep your pump primed. There's always fluid within your pump. No air pockets. Air pockets equals cavitation. Cavitation equals damaged pump. So that's the purpose of your check valve. Another one, your chiller valve assembly. Again, chiller valve assembly, same, almost similar to your air handling unit and fan coil unit valve assembly. Provided the difference is there's check valve here on the evaporator side. There's check valve on the evaporator side because this is a closed loop, open loop system. So there's a check valve for the evaporator. This is the closed loop system. There's a check valve here, and check valve here, and there's a metering device. This metering device measures the flow. Before, it's not common to put metering device on the chiller, but now it's very common to put metering device on your chiller, kind of like the balancing valve. But the difference is it doesn't restrict the flow, but only measures the flow. The balancing valve also measures the flow through pressure difference, but the metering measures the flow to ensure the chiller's efficiency. The control valve also measures the. Yes, sir. Any question? No question? All right. So based on the metering valve, based on the water flow rate going through the chiller, your control valve opens and closes as necessary. Right. So example, for equipments, for air handling units, for duty air handling units. The counterpart is 3 chillers, 2 duty, 1 standby. Okay. Option 1. So this air handling unit is turned off. What's going to happen? So either you can see either this 2 chiller lowers down, same, equal. So this is 1,500 kilowatt. This is also 1,500 kilowatt. Okay. Or option 2, this is running still at 100%, 1,000 kilowatt. And this is running at half, 500 kilowatt. Still, the total here, no change, 1,500 kilowatt. How are you going to do that? Okay. Again, this is your chiller. Your chiller has your temperature gauge, pressure differential, flexible connector. Same concept, same principle. Drain points for your installation purposes. Flexible connection uh, to isolate the vibration from the chiller to the rigid pipes. Okay, the flow meter. Okay, the flow meter is connected to your chiller, and this flow meter is connected to your chiller. This motorized valve is also connected to your chiller, and this temperature sensor is connected to your chiller. Usually, the chillers have their own control logic and control sequence. It's not on the BMS. Your BMS is only to monitor. Okay? This chiller, the engineers don't use logic. It's the manufacturer who makes the logic to ensure the efficiency of the chiller that they are selling. So example, you're buying from York or Train or Carrier. They have their own proprietary softwares, they have their own proprietary logics to ensure that their equipment, their chiller is running on top condition. However, your BMS can extract this data from your chiller units. So if you go to your chiller units now, you can see your chiller units have its own PLC, has its own display panels, has its own controls. It's not within the BMS. The BMS is there only to extract those data and to see and to monitor. But all these logics are not housed in the BMS, it's housed on your chiller. So the flow meter will go to your chiller PLC, and your chiller will tell the appropriate signal, will give the appropriate signals to your motorized valve. So your motorized valve will open or will close. Will open 50% or will open 75%. Your chiller will know. And this chiller, like what I said, it's controlled by proprietary softwares, and they are connected to each other also. So this chiller would know if the other chiller is running at 100% or if it's running at also at 75%. Okay. So that's it for our waterside controls. So we have learned how to control our air handling units or our airside, and we have learned how to control our waterside. So this is the control of your Acmv. Based on your set points, you can monitor different parameters, and you can control different field devices to get the set points that you need. Other auxiliary systems in the Acmv. Auxiliary systems means these systems are invaluable, needed to operate the Acmv system, but they are not adding to the performance, or they're not adding to the capabilities of your Acmv. So for example, your system is 100 kilowatt. You put your auxiliary system, your system will still be 100 kilowatt capacity. So no change. But they are invaluable to the operations of these Acmvs. So first, secondary drain pan for your air handling unit and fan coil unit. To prevent spill, there will be times that the equipment will fail. And the problem is you wouldn't know which equipment will fail, especially if this equipment is installed overhead. So when an equipment fails, to prevent or to early detect this failure, you put secondary drain pan. When water is leaking to the equipment, your secondary drain pan will capture it, and the secondary drain pan has this water leak sensor. So this water leak sensor will sense that there's water, sends an alarm telling that there's something wrong with this unit, with this specific unit. So secondary drain pans are important in installation, especially for overhang units. Another system, UV light. UV light uh, may question dito si, there's a question from Ferdinand. What's the difference between Acmv and Hvac? So Acmv is air conditioning and mechanical ventilation. Hvac is heating, ventilating, and air conditioning. So there's one process that we're taking away, the heating process. So Acmv is only air conditioning, which is cooling process. Hvac is heating and air conditioning. So there's one process that was taken out. Okay. All right. Another system for the air handling unit is the UV light. This UV light kills the bacteria. So sometimes because of moisture and cold temperature, bacteria grows within the coil. So one example is yung mold. One example is the molds. So this UV light prevents growth of bacteria within the coil. Another one is smoke detectors. Oh, these smoke detectors is very important, especially in Singapore, where smoke detectors are required to be installed inside air handling units. So it acts like a early warning fire protection. So when air is returned to the air handling unit, to prevent this smoke to be transferred to other areas, smoke detectors are installed. So when the air handling unit senses that there's smoke, the air handling unit stops to prevent the smoke to spread out further. Another system is the ionizers. Just like the UV light, the ionizers has ionizes the air so that the dirt and the bacteria dies and it will be clumped together so that it will be big enough to be sifted through or to be captured by your filters. So ionizers release negative ions so that the ions within the air, the dirt and the bacteria and the viruses will be clumped together and will be captured by your media filters or your filters. Another very important system is your auto air vent or your degasser. Now they uses degasser. Before when I install, I only use manual air vent. Now there's auto air vent. So this auto air vent removes the air within your piping system. Remember we mentioned earlier that air bubbles or air within the piping system is dangerous to your pump. Causes cavitation and it causes damage to your pump. So to remove the air within the piping, you have your auto air vent. You see it's installed on top of the pipe where air is lighter than water, so it will rest on top of the pipe, and this auto air vent will release those trapped air. Another system is the expansion tank. Don't forget the expansion tank for your chilled water system. This expansion tank absorbs the thermal expansion of the water. If you can remember the formula, PV is equal to nRT, where the volume of water is proportional to the increase, the change of volume of water is proportional to the change of temperature of water. So when cold water warms up, it expands. If you use your water cup or your glass, since the water quantity is small, the expansion seems negligible. But if your system is a big system, you may need expansion tanks because there's going to be a lot of water. And the change of temperature on those water will give you a significant increase in volume. So that increase in volume needs to be absorbed by something somewhere. And that's the purpose and that's the job of your expansion tank. Chemical dosing system. Chemical dosing system is for both your cooling tower and your chiller water. Since the inside your pipe is water flowing through steel pipe, sooner or later desalination and rust will happen, and this chemical dosing pump will ensure or will keep your water on a normal pH level. Another one is your auto tube cleaning system or auto tube cleaner for your chillers. So these auto tube cleaners is small balls that goes inside the tubes of your chiller. When the balls and the tubes come in contact, frictional force will help scratch the linings of your uh, chiller tubes, and it's being recycled, uh, making your chiller clean for much longer time and can be used for the maintenance period becomes much farther duration, longer frequency. Another one is the refrigerant leak detector system. Since your chillers have leaked, they also have compressors. They also are they are also using refrigerants. Sometimes there's refrigerant leaks. Refrigerant leaks are colorless and odorless deadly gas. So you would need refrigerant leak detector system around your chillers. Last one, like what we mentioned before, chemical dosing system for your cooling tower. So there's a different set of dosing system for your open loop and for your closed loop system. Basically, because your open loop is open to the atmosphere, which means the dirt and bacteria within the air can also be transferred to your water, which means you would need different chemicals needed for the dosing system of your cooling tower. Last one is your makeup water system. When your cooling tower operates, some of the water is being vaporized or being trickled down to your cooling tower. When outdoor air goes inside, some of the water are evaporated and some of the water goes with the air. So not all of the water that flows down goes back out. So to compensate for the loss of water, you have a makeup water system. So this makeup water tops up, ensuring that the water within the cooling tower is always at the optimum level. All right, so that's it. That's the auxiliary systems installed for your ACMV. So these auxiliary systems are needed for the operations of your ACMV system. However, they do not add to the cooling capacity of your total system, but they do help in maintaining and keeping the efficiency of your ACMV system. Thank you very much. So any questions? questions that I can answer for you guys? Wala naman?
Hello, sir. Good evening, sir.
Yes, sir. Sir Eric,
Yes, sir, good evening.
good evening.
Sir, how about for the air-cooled chiller, sir? Yung,
Air-cooled chiller. Okay.
ah, yung valve single niya, same ba sa water-cooled or iba?
Yes, same lang.
Okay, sir. Thank you.
Same lang. Any more question? Rodolfo asked how to calculate the diversity factor. Diversity factor of, I'm sorry, I need a more specific diversity factor of what? Sir Rodolfo? Sir Rodolfo, you can unmute yourself so you could ask your question. So wala na. All right. If there's no more question, then we will end this training. Thank you for participating to the last of the ACMV series. All right. So this is the last ACMV controls. Oh, teka, may question dito. Will you share this slide, sir? Yes. I will share this slide. For those who have registered, I will provide you the slides for this session. For Sir Rodolfo, your question you can send it to my email, evenlearning.sg@gmail.com, and I will try to answer your question. You may contact me directly so that you can clarify your question. Thank you very much. This is the last part of our ACMV series. For those who would want to watch all 5 recordings of the training sessions, they will be available in our Facebook page, Even Learning. Alternatively, you can also go to my YouTube channel, Donny Gabriel. It will also be available there. Our next training session will be in 2 weeks, January 30, titled ACMV Fundamentals. So we're done with the ACMV series. We'll start with ACMV Fundamentals, and the first one will be the psychrometric analysis. Be sure to refer to the event section of the Even Learning page. We appreciate we would appreciate it if you can help us improve our services by accomplishing our feedback form. The feedback form will be sent to you via email, and it will also be available through the link. Through the comment pala, sorry. It will also be available through the comment. So thank you again. Thank you for participating. We'll see you again on our next training session.